Our next speaker is Dr. Thomas Lockhart, and Utah is so fortunate to have Tom here at the Hill Air Force Base and part of our community, given his deep background and his expertise. He is currently he's a member of the Senior Executive Service. He's Director of Engineering and Technical Management, Air Force Nuclear Weapons Center, Hill Air Force Base. He enhances the warfighter support as the center's lead for nuclear systems and digital development technology and insertion, and multi-domain systems support for the Minuteman III and the launch of the cruise missile and command and control. And prior to coming back here to Utah to run this nuclear weapons center, he was a director with the Air Force Research Lab. So that's why you've heard his name several times today as someone who was a leader, a thought leader within AFRL. So Tom, I know that you're on, so welcome. And I've got your slides here. And let me put it into presentation mode, and I'll let you take it away.
Well, thank you for the opportunity to present today, and I really do. Can you hear me? Okay, first of all.
Yes, we hear you fine.
Perfect. Okay, I thought Crystal got in here earlier and set it up. Just to give you insight, what I was doing is I was meeting with the Secretary. The Secretary of the Air Force was out visiting Hill Air Force Base. So I thank you for letting me go last. Hopefully, it'll cap. I think Dr. Russell will be after me, but it'll kind of cap the day with some really good information. So, Utah Advanced Materials and Manufacturing Initiative is a very important to the Air and Space Force here at Utah. And so my presentation or my talk today is really about this digital research, innovation to support air and space. And it really kind of focuses in on system thinking and digital engineering and several of the areas that we've matured over time in the Air Force and now the Space Force. For anybody that hasn't met me, I'm Tom Lockhart. I am the Director of Engineering for the Nuke Weapons Center, but I'm also the Senior Functional out at Hill Air Force Base. And so that picture that you see on the chart itself is an aerial view of Hill Air Force Base. And just to give you kind of the size and the scope of work that's actually done there, we've got about 25,000 people plus, and we have over 4,000 scientists, engineers, and technical support staff that work at the base itself. And it's a broad range of experience, all the way from research and research in basic and applied into acquisition, buying products, and sustaining and supply chain management. And it covers air A-10s, old, they called them the warthogs, but old aircraft, F-16, all the way to the newest generations of F-22, F-35, and space and radars. So if you think about that, that is a very, very large portfolio, economic impacts of billions of dollars across the northern part of Utah. So let's go to the next chart. With every government presentation we have to, or military presentation, we usually put in, an overview. And really today, what I'd like to do is cover a little bit about Utah and some of the connective tissues that already exist with the base, and kind of run from north to south, and just areas that I see that are already doing innovative research. I'd be amiss if I didn't talk a little bit about our portfolio on the Air Force Nuclear Weapons Center. And why I want to do that is just show you why it's a big impact to Utah today and into the future. And then the last little takeaway from the overview is I really want to touch on 8 areas that I believe are, this group is enabling the future of the Air and Space Force. Okay, it looks like we already moved forward. And so why Utah? Why is Utah so important? And so I'm going to start in the northern tip of the state and in Cache Valley. If you get up there, Logan, You've got Utah State University, a real good partner with us in education and outreach, but they also have a group that's a university affiliated research center, and it's Space Dynamics Lab. And if you look at the work they're doing, they're leading a lot of the air and space research in small satellites and small, kind of commercial type entities. And so that's right in Cache Valley. So if you go over to the left, Box Elder and Tooele, we've got Utah Test and Training Range that's out there, Army Depot, and so there's a lot of really great work and ability to go out and look at the materials and the manufacturing and actually test this. It's largest contiguous running test range in the United States. So it runs all the way from Utah through Nevada to California. So that's very important. If you go into Weber State University, and they've been just a great partner. I talked about 25,000 people, 4,000 engineers. They've been just a phenomenal partner as we kind of build out, legacy aircraft, legacy spacecraft, also radars and so forth. But they've been an invaluable partner. And so now getting into Salt Lake with the new airport, if you actually go down there, there's a lot of big businesses as you kind of trickle down by the airport, Harris, but both Salt Lake Community College and University of Utah have been really great working composites, additive manufacturing, and really some of the tough questions that we've got to deal with in the materials manufacturing. And I call it the physics-based modeling. And so hopefully Dr. Bunning, Ms. Timothychik, and then probably Dr. Russell after I get done, they'll talk about the importance of integrated computational materials science and engineering and how those things work together and how do we understand that in order for us to ensure, in our case, aircraft airworthiness, and the nuclear side, nuke surety, to make sure it's the level that we expect it to. Down past Salt Lake into and on, if you actually, we call it the Silicon Slopes. And it's just a whole bunch of software and software development capabilities. I think Adobe's there, Dell, etc. And it really is now this digital ecosystem that I'm going to talk about. And it really is so important to have this in order for us to generate this innovative, novel way of doing materials and manufacturing. And so the two bullets on here, Utah business infrastructure, you think about the airport and what's been done there and the advancement of that airport is really important. The corridors across the state, I-15, I-80, they're advancing on ramps, off ramps. So we have the business infrastructure. And then the really thing that I'm going to push a little bit today is this Utah digital network. We're becoming a digital state, and it's very important for the work that this group is actually undertaking because it really is advanced materials and manufacturing, and you really have to have the ability to understand that. And this digital network actually provides it to us. Okay, next chart. The next chart that's coming up. So the Air Force Nuclear Weapon System Center and these are the systems, and I've highlighted in kind of orange, Utah is critical for our success. And so I'll start on the left-hand side. Utah has been an invaluable partner for us for a long time, and it's been on what's called Minuteman 3. And on the far left, it says W78, W87. That's just nomenclature in the Air Force for the weapon itself. And that's the air vehicle equipment. They call it the flight system. As you kind of migrate to the middle, it's more than just the air vehicle equipment. It's launch facilities, launch control centers, transportation and handling. We have a whole fleet of trucks that we actually have to move components to and from the various bases in Wyoming, in Montana, in North Dakota. So we've got that. And then across the top is how do you actually command and control and communicate with those various locations. And then on the right-hand side, it talks about weapons, and aircraft interface. So Utah, 2/3 of the nuclear triad is really somewhat maintained here in Utah. And you think throughout these different weapon systems that I just hit, the materials that have to be understood, the manufacturing process that have to be consistent, and we've got it all the way throughout this portfolio. And I've identified our large ACAT, which is acquisition category ones, which are multi-billion-dollar programs, ground-based strategic deterrent. Uh, it's very large, and it's a replacement program for the Minuteman III. And then on the right-hand side, you've got highlighted some aircraft that are actually maintained here, so they're outlined. And then in the middle, in the purple, shows some of the weapons themselves. Gravity weapons, B-6112 is a tail kit assembly. It's a gravity weapon. And then air launch cruise missile is another weapon. And we've got a big program called long range standoff weapons that's actually replacing the air launch cruise missile. But this is all important for Utah because there is materials work that needs to be done in these areas. If you just look at Minuteman on the far left, that air vehicle equipment, composite casings, right? Engine nozzle ducts that are actually metals, specialized components that have to be additively manufactured. Those are all things that would be considered as part of this Materials and Manufacturing Institute. So let's go to the next chart. So I thought this was really important. I hope Dr. Bunning talked a little bit about that, but where is the Air Force today and where does it need to go into the future? And that's both air and space. And where does this Utah Advanced Manufacturing Materials really play? In the top, it says National Defense Strategy, National Security Innovation Base. And so we need to make sure we're postured correctly, that we can kind of take care of the weapon systems. And if you start, that's actually a timeline back to World War One, and the Wright Flyer is really the first aircraft where it was balsa wood and fabric that was actually being done. And how do we actually make that thing fly? And then over time, you see these peaks and valleys where we generated a lot of different. So right after World War One, we had a lot of activities on advancing aircraft. And then between wars, it kind of slowed down. Then World War II, it happened that we had a lot more aircraft that we had to maintain and different capabilities. So we had fighters, we had bombers, we had cargo, and all needed different material composition. The faster you fly, the different types of materials you actually needed. And then you kind of go into the Cold War era where we had, like ICBMs and missiles and Missile Defense Agency. And then for the last few years, it has actually kind of narrowed down. And so we had limited numbers, limited quantities, but it is changing. And so we're trying to figure out how to ensure that we keep up and keep a competitive edge with a near peer or a peer adversaries. That national defense strategy and national security innovation base kind of shows you those peaks and valleys over time, which is really important. And here's the 8 items that I just hope you kind of take away from my presentation of areas that we're interested in and important for materials and manufacturing. The first, and I'm sure you've heard it throughout the day, is additive. We've designed things in the past with subtractive manufacturing process. We set up for the industrial age and we did big manufacturing. Today, it's unique. Things are changing. And so the 2 pictures I have in there, one is just an item where it shows different material orientation and different material composition and how you can put that together. The second one, that dome that's kind of silver, shows you that we're starting to blend as part of additive functional materials, so things that are smart, with structural materials and coming up with different compositions. And so that's interesting. And with the research side of the house, and hopefully Dr. Russell and Dr. Bunning talked about it, getting to the point where electronics, now you have the ability to use materials and manufacturing that are actually flexible. So they can actually move back and forth like flexible electronics instead of having a hard case computer. Wouldn't it be nice to have that component linked into your actual jacket and actually keep control of it on your jacket itself? That's one. I'll work the alternate navigations. So most of the time you get up in the morning, if you're going to drive to work, you're going to drive across the state, you grab your phone, you plug in a MapQuest or Google Maps where you want to go, and you kind of run the course. And it's all linked in with our current satellites, our GPS, our global positioning system, and it gives you that information as you kind of move across. Well, what happens when that's not available? And so can you actually figure out different signals or opportunity that you can actually augment that and put together in such a way that you actually know where you're going and you didn't have to have satellite connection all the time every time. And so uh, we're looking at materials for positioning, navigation, and timing. And so there's new compositions in all three of those areas that we need to pay attention to. And in the future, there's a lot of conversations about quantum. And in my mind, quantum people jump to quantum computing. How do we make computers go faster? I think quantum's really novel in this area. So position, navigation, and timing, the quantum sensing, quantum encryption, et cetera. So I think that's interesting, an area that really needs that additional work. Uh, Network capabilities. So just talked about kind of manufacturing process and some new novel ideas on navigation, but now with these new networks, and I didn't say this but I probably should have, is University of Utah is the 5G network hub, and they're trying to do a smart city, but we're getting new network capabilities, and so we can share things with the cloud, connectivity and high bandwidth, things that we hadn't done before in the past. And I think that's really important for the materials community, because we did have a materials genome edition defining the materials, but we didn't have the network or the infrastructure to communicate those with this crowdsourced environment. And so now we're getting to the point where we have the connectivity and the data that we can actually put together, and I'll call it crowdsourcing, but the ability to kind of use whoever the subject matter expert is in that specific area to go work on those elements. And this one also just in network, the optics side of the house, new materials, uh, dense wave, dual multiplexing, the ability to kind of communicate back and forth across the network, really some novel ideas there, et cetera. Many targets and layers that we actually have to kind of go after and understand. And networks and spectrum management, I think there was some questions about cyber and cybersecurity. Obviously, as we aggregate, get to the cloud, connect things together, worldwide coverage, we've got to pay attention to that. And so some of the things that we can manipulate and understand on the lower end is really important for us in that network and spectrum management side of the house, waveform protections, etc. I'm going to jump down to the far left hand side, and it really is on the space. Uh, if you've been watching, there's a lot of commercial space activities today. Web One, SpaceX. I think I've seen articles that have gone upwards to 2 to 3,000 satellites. And I mentioned the Space Dynamics Lab that's up there at Utah State. Very interesting kind of dynamics. One of the leaders in these smaller CubeSat type activities, and how do you put a lot of them out up there quickly? But I think we're just at the forefront of understanding the abilities in commercial space. So it'd be great. You have, let's say 3,000 satellites up there, all staring down at the Earth. Think about what you could actually see around the world, what's happening, news, and et cetera. Um, Communication, it would be like an internet in the sky, the ability to go across from one of these satellites to the next. So I think there's a lot. And then really the design aspects for this materials and manufacturing. Think about structural materials with smart materials in there, like a battery that's actually printed into a satellite. Um, Open standards, the ability to make changes over time for satellites. A lot of times we thought we'd launch, we leave it, and then eventually it'll come back in, burn itself out, and it's done. But now, what about logistics? Could we actually go up there and change out solar cells? Could we actually refuel, et cetera? And a logistics arm to actually do that. And so I think space, and part of the reason I wanted to give this presentation, I think there's a lot of areas in the materials and manufacturing side of the house that really we can target to help out our space community today. Getting into the smaller scale, the nanotechnology and energetics, as you kind of manipulate carbon nanotubes, carbon nanofibers, first of all, in the United States, we really need to be able to do better on carbon nanofibers. I think a lot of our carbon nanofibers are actually being imported from a company in Toray, Japan. And so we've got to get better on how to produce that and actually utilize it. But it's actually with carbon nanotubes and carbon nanofibers, the ability to manipulate those things in a different manner. And it's really interesting to kind of see what we can actually do there. I did put energetics also at that scale. Oops, this app may be dangerous. No. Okay, I've stopped there. Okay, I saw a note. Hopefully, I didn't lose you guys. Is everybody good? Belinda, still
Yeah,
good?
we're fine. I don't know what you saw. We just see your presentation.
Okay, it pushed me up, said this is dangerous. Do not do anything. And so I stopped right there. Okay, let me finish up with energetics. The ability to manipulate things at the lower scale. You have the ability to make it burn fast or burn slow, depending on how you orient the energetics itself. Human performance, we've really got to now take that understanding at the lower level and be able to bring it up. And for the Air Force at the mission campaign, what happens when you use a different material composition at the physics level? What happens at the mission campaign? And we're linking things together. And so really, in the past, because of our networks and our capabilities to kind of link those physics-based models into the mission campaign, it didn't exist. And now we're starting to get there. And that's where I introduced that integrated computational material science and engineering ability. And to get off the kind of stage here is we're moving into an era where digital engineering has the ability to go up and down the chain depending on what the customer needs are. And so the next couple charts is really where I've been pushing the Air Force and the Space Force to kind of move into it. And we call it digital engineering. It really model-based system engineering, the ability to actually look at different, if you're a material scientist, a mechanical engineer, establish those relationships, change data, understand data, and put it up to the level and visualize it at the mission campaign. In our case, it'd be like an aircraft flying in a certain area of the world, the spacecraft, orbiting the Earth, and making sure we understand that. So let's go to the next chart. So this digital side of the house, we've been in the Air Force doing acquisitions the same almost since the 90s. We've changed a few things, but it really has significantly changed here in the last year, 2 years, because of the capability the cloud has actually provided and the network that I've been talking about. And so I'm going to just kind of walk you through this. I call it integrated digital ecosystems, milestones, and processes. So when you see MS, that's a milestone. And what we use for terminology. So milestone A, if you're thinking about research, it's usually at the basic and applied level. And then when we get to milestone B, if you're actually starting to build something into an application, and then when you get to milestone C, you're actually getting into productionizing it and manufacturing. So just to kind of level set what the terminology here, but it's a digital ecosystem, cloud enabled, with this model based system engineering, the ability to model things and capture the product over its life cycle and perform analytics. So you think about most of our products today, at least on the phones and stuff like that, they're designed for about 24 to 48 months. And you've got to actually understand that length of time. And in the past, with an aircraft, we just automatically defaulted to 20 years, 20,000 miles. Now we're trying to figure out low cost, attritable type items. And so we've got to understand the model based tools, that's the middle, and the capture, the environment, and the life cycle of the system. And so we go from understanding the basic and applied research, showing what it actually can perform to. Now, when we go out to you industry and our academic partners, is really start providing what is called a higher level architecture, but they call it model-based system engineering, system architecture. So we're providing those types of higher level architectures so you can actually build to And then so once you get into production, you're actually starting to capture data as you manufacture. So manufacturing, you have tolerance bands. And so the materials may be right at the edge. So the first time that it gets over 20,000 miles, it's going to fail. Or in other cases, you've over designed it so it could last to 30,000 miles. And so we capture that manufacturing data and understand that so we can actually predict the life when it's been used in these environments. And so the milestone C, system development and production, into system life, we actually capture that data. Leaving it open with MBSC, you have open standards. So over time, this is probably going to change. The customer will want something different. And you have the ability to kind of put into the model those changes and have a supply chain that actually can provide those different materials and manufactured components. So, okay, that's kind of system lifecycle, and hopefully you get an idea. This is where we're going from an Air Force perspective. Is this integrated digital ecosystem, cloud enabled, with the ability to do modeling up front to understand it, capture the data over the life, and be able to do the analysis and visualization at any level. You could have a pilot understanding all the way down to a scientist. Okay, next. And this is my last one is how do this integrated digital environment tools play nicely together? And so you can actually start doing that, material composition all the way through product design into sustainment. And so I put this model in the middle. I really think it is the heartbeat. It really starts tying together disparate functions like electrical, mechanical, materials, and that kind of stuff, but it captures that architecture. So you really have the bone structure of what needs to be produced. And we're starting to build those out. We're starting to train our system engineers to understand how to put together this government reference architecture. Also, how do you validate and verify those disparate type relationships? That middle section is model-based system engineering and the ability to put the model together and relate those different functions together. Then we branch off to actually see on the right hand side, it says operational analysis. So you built the architecture, you want to see how it executes over time. And so from a material standpoint, you kind of understand materials decay at a certain rate. Composites are actually a step function. It looks good for a long duration, and then all of a sudden it breaks and it has a problem. But with metals, you can kind of see over time. So operationally, how well it can actually perform with slight degradation all the way till disruption where something actually occurs. Behavioral models and algorithms, so we can actually calculate those things and get prognostics and predictive algorithms to actually understand that. The trade space, so we could actually see, maybe we want to leave this open. We recognize that there may be a change in technology, maybe that we're going to actually have to replace it anyway and bring it in for maintenance. So we need to kind of pay attention to that. But it's that trade space analysis in the performance itself. You don't want to interrupt the customer from doing its day-to-day job, but you want to also ensure that it's kept current and understood. The product lifecycle is the modeling, and then you capture that all the way from the top level system down to the materials, the physics based, and so you can actually link those together. Software, we recognize all these tools today don't really nicely play together, but they're out on the cloud, and so we're putting the middleware together to actually figure out how to take portions. The physics-based model usually run on a high-performance computing system, and you probably just want results to actually present to the system guys. And so you don't want the whole model in their actual MBSE tool. And so we're putting this software middleware together for the analysis and linkage up and down, and for, I call it authoritative data, the ability to understand what was actually provided, because at some point with aircraft, you have to certify, qualify, and there's a type certificate, and you have to be able to convince the airworthiness authorities it actually works, and that allows us to kind of connect the models with some of those more detailed physics-based tools. And then obviously, anytime you're dealing with manufacturing and materials, you've got to have cost trades. Hey, we may want to last longer, we want to last less because they're going to bring it in for change of oil and tires, brakes, and that kind of stuff. Or do you want to make it last longer and then charge more? And so that's the cost analysis. And then the last little piece is just tracing to the original requirements. But this is all what we're talking about in this integrated computational material science and engineering all the way up the chain. And then the last little piece, the blue box around all of this is the ability to take this out of our standard way of looking at things and being able to visualize it. And you have to really relate to the human on that one, the human eye. So augmented reality, virtual reality to kind of bring that up. Okay, I think that's my last chart. Sorry, it took me a little longer. I got interrupted there. So we'll just go to questions. Let's go ahead and go up one and we'll just go to questions. Is there anything that anybody would like to ask?
Thank you, Tom. That was a fabulous overview. Really appreciate your insights and providing such a comprehensive view.